In multivariable calculus, some concepts are so powerful they almost feel like a magic trick. Well, today we're going to pull back the curtain on one of the most elegant and frankly useful theorems of them all, Stokes' theorem. So, what does a simple soap bubble have to do with any of this? It might sound a little out there, but stick with me here. Imagine you've got a wire loop, right? And you dip it into some soap solution. That shimmering film that forms inside the loop. That holds the entire secret to understanding Stokes' theorem. It's the perfect real-world picture for a really profound mathematical idea. At its very heart, Stokes' theorem is all about connecting two totally different ways of measuring things in 3D space. You can think of it like a tale of two worlds. First, you've got the one-dimensional world of the edge, or the boundary, that wire loop. And then you have the two-dimensional world of the surface stretched across it, like our soap film. So on one hand, we could walk along that wire loop, that boundary, and measure the total spin or circulation of some force field all the way around. We call that a line integral. But on the other hand, we could just ignore the loop itself and instead look at that soap film, the surface, and add up all the tiny little swirls of that same force field at every single point on the film. That's a surface integral. So the big question Stokes' theorem asks is, are these two completely different measurements actually related? And yeah, you probably guessed it. They're not just related, they are exactly the same. Stokes' theorem is the mathematical bridge that connects these two worlds. It proves, without a doubt, that the total measurement you get on the edge is always equal to the summed-up measurement across the surface. Now, the key ingredient for the surface side of this bridge is a little something called curl. The best way to think about it is this. Imagine you drop a microscopic little paddle wheel into a flowing river. The curl, right at that spot, tells you exactly how fast and in what direction that tiny paddle wheel would be spinning. It's the measure of the micro-rotation at every single point on our surface. And here it is. This is the bridge. On the left side, you've got the line integral around the closed curve C. That's the total circulation on the boundary. And on the right, you've got the surface integral over any surface S that has that boundary. This side adds up the curl, all those tiny little swirls across the entire surface. And Stokes' theorem says, these two things, they're equal, period. Now, for this bridge to actually work, there is one absolutely golden rule you cannot forget: orientation. Both sides of the equation have to agree on which way is up. The right-hand rule is going to be your best friend here. Just curl the fingers of your right hand in the same direction you're traveling around the boundary loop. Whichever way your thumb points, that's the positive direction for the surface. If you get this wrong, your whole answer will be off by a minus sign, so you gotta get it right. Okay, enough with the theory. The real power of Stokes' theorem is that it can turn a ridiculously hard problem into a much, much easier one. Let's see it in action. For our first example, we're going to use it as a strategic shortcut. So, we're asked to calculate a line integral, but as this quote from Baker's math class perfectly puts it, trying to describe this specific curve mathematically, parameterizing it, is just annoying. It's a real pain. So what's the strategy? Don't do it. Forget the hard line integral. Let's use Stokes to switch over to a surface integral and see if that's any easier. Okay, here's the game plan. First, we calculate the curl of our vector field, f. Turns out it's pretty simple. Second, we pick the easiest possible surface that has our annoying curve as its boundary, which in this case is just the flat elliptical disk that sits on the plane z equals 2 minus y. Third, we find the normal vector to that plane. And finally, we set up our surface integral. We integrate the dot product of the curl and that normal vector. And look at that, it simplifies all the way down to just integrating 1 plus 2y. And this is where the strategy just pays off big time. When we integrate 1 plus 2y over a circular domain, we can use symmetry. Think about it. For every positive y value, there's a matching negative y on the opposite side of the disk. So when you add them all up, that whole 2y part just cancels itself out to 0. We're just left integrating the number 1 over the area of the disk. And what's that? It's just the area of the disk. The answer is pi. See, that is the power of Stokes' theorem. It turned a really messy path into a super simple area calculation. I know, that was impressive. But you might be thinking, does it really work every time? Well, let's prove it to ourselves. In this second example, we're going to verify the theorem by actually calculating both sides of the equation from scratch and showing that we get the exact same answer. So here's the setup. We've got a vector field f, and our surface is the top half of a sphere, a hemisphere. The boundary of this hemisphere, of course, is the unit circle just sitting on the xy plane. All right, first, let's do this the hard way. Let's tackle the line integral side. We parameterize the boundary, that unit circle, in the standard way with sine and cosine. We plug all of that into our line integral formula, and after a little bit of algebra, the whole problem boils down to just integrating cosine squared of t from 0 to 2 pi. Now, for any of you who remember this integral from class, you'll know right away the answer is pi. So our line integral, the measurement along the boundary, gives us a value of pi. Okay, let's pin that. Now for the moment of truth. Does the surface integral give us the same thing? All right, time for the surface integral side. First, we compute the curl of our vector field, which, amazingly, just comes out to the constant vector 1, 1, 1. Super simple. Then we integrate the dot product of this curl with the normal vector over the whole hemisphere. And once again, something beautiful happens with symmetry. The integrals with x and y just drop out, and we're left with just the surface integral of z. And the value of that integral? You might even recognize it from a center of mass calculation. It's also pi. They match perfectly. The total circulation around that 1D boundary is absolutely identical to the sum of all the little swirls on the 2D surface. The bridge between the two worlds is solid. The theorem works. So what does this all mean for you as you're working through these problems? Stokes' theorem isn't just another formula to memorize for the test. It is a new tool in your problem-solving toolkit. It's a genuine calculus superpower. Let's just wrap up the key ideas. At its core, Stokes connects the 1D world of the boundary to the 2D world of the surface. But its real magic is that it lets you choose the easier path. You can swap a hard line integral for an easy surface integral, or even the other way around sometimes. And if you know Green's theorem from 2D, you can think of Stokes as its bigger, more powerful 3D sibling. And please, I'm saying it one last time, never ever forget to check your orientation with the right-hand rule. And that right there, that's the real takeaway. Stokes' theorem gives you a choice. It gives you the power to look at a single problem from two totally different angles, and then pick the one that's simpler, more elegant, and just plain faster. So the next time you're staring down a complex integral, remember, you can bridge these two worlds. Which path will you choose?